We'll talk about holographic space reconstruction and related topics. Daniel?
Okay, you can hear me? Yeah, okay. Thanks, like everyone says, to the organizers. It's been a fun conference. Thanks also to Douglas for going last so that at least one of the talks I can enjoy without being nervous. I also gave a vision talk last year, and that one was kind of more philosophical about the state of the field. Do I have a clicker or something somewhere? Oh, here, I see. Sorry. Yeah. But it's a. Oh, yeah, it works. Okay. I didn't want to repeat myself, and my vision doesn't change that fast. So today I'm going to give a talk that's a little bit more concrete, more about, well, not quite a technical talk, but more detailed things. If you want to hear the philosophical things, you can go look at the video from last year. I'm going to start by saying that, well, I think that ADS-CFT is the most remarkable result which has come out of string theory so far. It tells us that non-perturbative quantum gravity in asymptotically anti-de Sitter space seems like this complicated thing is really equivalent to just, plain old, well, I shouldn't call it boring, but relatively simple quantum field theory in disguise. Okay. Now, at the most primitive level, the ADS-CFT correspondence, you can just think of it as saying that there's an isomorphism between the Hilbert space of the bulk and the Hilbert space of the boundary. This doesn't, there we go, it works 50% of the time. In quantum field theory on spatial sphere, knowing the Hilbert space is the same as knowing the set of local operators, so we can describe the correspondence by saying how it acts on local operators. And the way that we do that, or one way, which I like, is to use this extrapolate dictionary, which says that if you've got a CFT local operator, then you can interpret it as the limit of a bulk operator, which is pulled to the boundary, where we take the R going to infinity limit, and wherever it ends up on the boundary, that's the local operator. Now, strictly speaking, for this to work for all the local operators, in the bulk, we need to include things that create bound states and black holes and this kind of thing. So things that Hiroshi and I called quasi-local operators in our paper. This extrapolate dictionary is pretty good if all that you want to talk about are scattering kind of experiments. For example, here's some scattering experiment where we do 2-to-2 scattering in the bulk. I'm simplifying a little bit here in this. And we can just recast that in terms of 4-point functions of local operators in the CFT, which is kind of the bread and butter of any person who thinks about CFT. And in particular, this extrapolate dictionary is sufficient, at least in principle, to think about things like the formation and evaporation of small black holes, and also maybe a little more practically to think about this 2-point function version of the black hole information problem, which Juan explained to us, where you look at very long times in the 2-point function and study its long time behavior. Now, one sometimes hears, and certainly I was often told as a graduate student, that these scattering kind of questions are really the only ones that you should be talking about in quantum gravity. And I was told that for a reason, which is that so far at least, these seem to be the only ones which we really know how to formulate mathematically precisely. But fortunately or unfortunately, there are many interesting questions which, at least so far, we don't know how to describe in this way. So let me give you an example. So this is well, you can think of it either as a one-sided black hole with this being different sides of the sphere, or you can think of it as the two-sided ADS black hole. So we can throw these two things into the black hole, and they scatter, and we want to know what comes out. Now, I don't know how to recast that as a CFT correlation function, because the problem is all this stuff in the final state ends up in the singularity and doesn't make it back out to infinity. But if we say that ADS-CFT is a complete theory of quantum gravity in anti-de Sitter space, then this kind of question is a question that it owes us an answer to. And until we can provide that answer, we don't really get to say that we understand quantum gravity in ADS through ADS-CFT. Now, there's a program for trying to answer questions like this, which is called bulk reconstruction. I don't know why it's called reconstruction. You know, it's like recombination in the CMB. I mean, it's just some funny historical thing. Anyways, that's what it's called. So the idea of bulk reconstruction is that you want to back off of that limit in the extrapolate dictionary, and you want to talk about these operators in the bulk, directly in the middle of the bulk. You want to represent them as operators directly on the CFT Hilbert space. And of course, you have to deal with the fact that there aren't really bulk local operators, so you have to make them diffeomorphism invariant. And that's not something I'm going to discuss in detail in this talk. Now, these representations are always going to have some kind of inherent imprecision, because in the end, bulk effective field theory is not really what's going on in the bulk, right? I mean, at least there's probably, we think, strings and branes and so on, and ultimately the theory is really the CFT. So we'll probably have to live with the, this bulk reconstruction program will have to live with the idea that this phi's that we represent will have a little bit of vagueness in them. We won't, be sure quite exactly what we mean. But on the other hand, at least in ordinary situations, this imprecision really seems rather small. For example, well, we have gravity in our world, but nonetheless we use quantum field theory at the LHC, and it does a pretty good job. We've certainly never seen any deviations from quantum field theory in our world, even though maybe we think that ultimately it's holographic. So somehow, what we want to understand is how this d-dimensional CFT on the boundary can pretend to be a d+1 dimensional gravity theory in the bulk to a very good approximation, at least in a restricted set of situations. So that's somehow the problem that bulk reconstruction is trying to solve. The first strategy for doing bulk reconstruction is based on what you might think of as just kind of the stupidest thing possible. So you just take the bulk equations of motion, effective field theory equations of motion, and you just perturbatively solve them using the extrapolate dictionary to provide the boundary conditions. So since the extrapolate dictionary tells you every bulk object, it tells you what its limit is on the boundary, then if you have some PDE, that's a boundary value problem, and you can try to solve it inwards. So when you do that, this leads to formulas that look like this. It doesn't really matter the details of the formula. I just wanted to write, well, this is the term people usually write, and then I wanted the interaction just so you know that you can include interactions. And then you can show, then you can show that the operators that you construct this way obey the algebra and reproduce the correlators of bulk effective field theory, at least for order 1 numbers of operators in the vicinity of the vacuum. So at least in this kind of very restricted situation, you can complete the bulk reconstruction program just by using this, solving the classical equations of motion. But I should say that it would really be a pity if that was all there was to holography. Like, wouldn't that be kind of disappointing if you're just like solving the PDE? I mean, holography feels deeper than that. And indeed, we'll see in a little bit that this method is really not able to describe regions of space-time which are behind causal horizons. And that's the problem that we really want to solve, right? The stuff that's not behind the causal horizons, why do this anyway? You can just look at the scattering experiment. Now, in the last few years, there's been a lot of progress on this idea of bulk reconstruction. And at least from my point of view, at least one of the real key ideas that led to that progress was this idea of subregion duality, which was a proposal given in a couple papers by these people, where they suggested that not only is the boundary CFT dual to the bulk, if you have access just to a spatial subregion of the boundary CFT, there should actually be some spatial subregion in the bulk which is dual to it, in the sense that any question about things within that subregion, you can learn the answer just by using the degrees of freedom in the boundary subregion. And it wasn't totally obvious whether that should be true necessarily. There was some sort of circumstantial evidence, which is what led these people to suggest it. Now, once you have this idea, there's a there's a natural subregion to consider, at least from the point of view of this strategy of solving the bulk equations of motion. And the region that you consider is called the causal wedge. So I wrote the definition here. This is kind of relativist terminology, so let me just say it. So the idea is, so say this R here, so a spatial subregion here, I'm in 2 + 1 dimensions, so a boundary spatial subregion is like this interval here, a little bit more than half the circle. The idea is I take its domain of dependence in the boundary, that's this D of R, so that's like the causal diamond of this region, and then I take the intersection in the bulk of its future and its past. And so if you think about it for a little bit, you can convince yourself that if your tool is solving the bulk equations of motion, this kind of almost has to be the right region to consider. For example, like I could, by changing the boundary conditions here a little bit, I could kind of send in a little spaceship that could fly over here and figure out what's going on, and then it could send a report back to me up here. And so since I can describe that experiment just using these degrees of freedom, I should be able to figure out what's going on, at least in this region. Now, this idea, though, that this CR, this causal wedge, is the right bulk subregion to be dual to R, is actually, it's called into question by the other main insight that has led to this project, to the recent progress, which is the Ruta-Kianagi formula. And so here's my attempt to explain the Ruta-Kianagi formula with the picture. So again, we have some subregion R. So this wedge, it maybe doesn't look that different from the other one, although I was careful to have the null geodesics focus up here. It took a lot of time, actually. That used up the whole CGI budget for this talk. So the idea is you take the boundary of the region, and you look for a codimension 2 surface, which here is just a geodesic of extremal area, whose boundary is equal to the boundary of R, and which is also homologous to R. So it means there's a partial Cauchy slice here in between gamma R and R, which I guess I've called capital C. I think that's what that is. And then what the Ruta-Kianagi formula says, and then this WR, this wedge, is the bulk domain of dependence of this partial Cauchy slice chi. And that's called the entanglement wedge, this WR. So then what the Ruta-Kianagi formula says is that if you want to know in the von Neumann entropy of some state in the CFT, restricted to this subregion R, then what you're supposed to do is you're supposed to take the expectation value of the area operator on this extremal surface divided by 4G, and then if you're working to next to leading order in G Newton, then you're supposed to add to that the bulk von Neumann entropy of the degrees of freedom that are living inside of this entanglement wedge, WR. Now, the reason why this seems to suggest that this causal wedge is somehow not good enough is that there's a general result from Wall and then from these people that the causal wedge is always contained in the entanglement wedge, and moreover, it's generically a proper subset. And in particular, this HRT surface, the gamma R here, is typically not in the causal wedge. But nonetheless, I can just take the boundary degrees of freedom in this subregion, and I can compute the von Neumann entropy. And now, for example, it's telling me about the area of that surface. So it's at least telling me about something which is outside of the causal wedge. Okay. So this was kind of a tantalizing hint that maybe indeed there's something more than solving these classical equations going on here in holography. Now, the nicest possible consequence of this would be that actually not only does the CFT know about the area of the extremal surface, it knows about all of the degrees of freedom in the entanglement wedge. If you have all the operators in the CFT just in R, then you can learn everything about the bulk throughout this entire entanglement wedge. So that idea is called entanglement wedge reconstruction. This idea of entanglement wedge reconstruction is very important, and I want to emphasize why. So if you think about the definition of the causal wedge can never contain any points behind an event horizon, because it has to contain points that are in both the future and the past of part of the boundary, right? And anything that's behind a horizon is either not going to be in the future or the past, or maybe both of the boundary. So if the causal wedge is all there was, then it would somehow be saying that the CFT is kind of only dual to the stuff that's outside of the black hole. Okay, and that, I guess it could have been true. Some people did suggest that, but it would have been rather unsatisfying. But of course, this is not true for the entanglement wedge, and here's an example. So this is one of these longer, elongated wormholes that Aaron talked about in his lecture this morning. And so in this example, the entanglement wedge is this light blue region, well, I guess the union of the light blue and the dark blue, whereas the causal wedge is just the dark blue. Here we're talking about the entanglement and causal wedges of just one of the two disconnected components of the boundary. So if entanglement wedge reconstruction is correct, it tells us that at least in some cases, we can reconstruct degrees of freedom that are inside of black holes using ADS-CFT. So the stakes are high. In 2014, with Ahmed, who was the last speaker, I guess, right before lunch, and also with Xidong, we pointed out that this question of subregion duality was an example of a more general phenomenon which in quantum information theory was very well known and which is called quantum error correction. And don't worry, I'm not going to try to tell you anything about quantum error correction in this talk. But anyways, we argued that once you understood that quantum error correction was what was going on here, that somehow you must be able to, or you should be able to resolve this question of whether or not the entanglement wedge reconstruction is correct by making use of the technical machinery of quantum error correction. And in fact, since then, that has worked out. So, well, there have been a bunch of results. I'm just going to mention 3 of them, which are perhaps, well, certainly I think they're certainly at least among the most interesting. So the first is that indeed, entanglement wedge reconstruction is a direct consequence of the Ruta-Yanagi formula. You can't have the Ruta-Yanagi formula be true without having entanglement wedge reconstruction. And moreover, in fact, they're equivalent. So if you have entanglement wedge reconstruction, then you must have some kind of Ruta-Yanagi formula. And then moreover, since there's an independent argument for the RT formula due to Lukowitz and Maldacena for the first version, and then later Faulkner, Lukowitz, Maldacena, and then also Rangamani and Dong and Lukowitz and Dong and Lukowitz, and by now all sorts of iterations have been established using the same basic idea. And that means that this entanglement wedge reconstruction really is a true property of ADS-CFT. Okay, and that was probably the most sort of concrete thing that was learned from this idea. There's something more qualitative, which, at least for me, was very enlightening, which is that this idea, in ADS-CFT, right, when I was a student, that, was the puzzling thing about ADS-CFT? It was the emergence of the radial direction. Where does the, you have this locality, spatial locality on the boundary, but then where does this local direction, radial direction come from? And people said various things, It's the renormalization group, it comes from Wilson loops, all sorts of things that you heard. But I would say really, based on this idea, I feel like this has really been, at least qualitatively and almost quantitatively explained using this language of quantum error correction. You just say that you talk about the degree of protection of logical degrees of freedom from erasures. And not only is this it sounds like words, but you can explicitly confirm this in exactly soluble models. And so maybe this is controversial, but I'll say it anyway. I would say that I feel now that our understanding of the emergence of the radial direction in ADS-CFT, I think it's comparable to the understanding of confinement after Wilson's paper. He didn't solve everything. There are still things that we don't understand. But there was a qualitative picture, and there was a solvable model where that realized the qualitative picture in a way that I guess probably most of us think is basically correct. One other general result I wanted to mention more recently with Oguri-san, we were able to use these ideas to show that in ADS-CFT there can't be global symmetries in the bulk. All right. Now, let me say a little bit more about the mechanism for how this works. The basic idea is that in any quantum error correcting code, you have information that you want to protect, and you store it non-locally in the entanglement between many physical degrees of freedom, and how they're entangled with each other. That's where you put the information, and that's what protects it, from some, annoying phonon that's going to come in and decohere your quantum computer. Now, there's a whole framework about, how and when this is possible, and I think one way to think about it is, there was this old proposal, well, not that old, but really remarkable proposal of Van Rumstonk that we should think of geometry as emerging from entanglement. And sometimes that sounds like a slogan, But I would say quantum error correction is really the mathematics of that. It's the mathematics of how geometry emerges from entanglement. And as emphasized by Mark, and then also later by Juan and Lenny, this phenomenon really, it's especially remarkable when we think about the CFT on a disconnected space. Indeed, it leads to this really outrageous statement, which is that in quantum gravity, it's possible for decoupled quantum systems to be dual to a geometry where there's a shared interior that you can access from observers from different systems can simultaneously access. You know, now, I mean, this was implicit in Juan's paper from 2001, if you read it, but it's really crazy, you know, and it's really an incredible thing. And I think it's really only in the last few years that at least most of us, maybe not Juan, but, you know, the rest of us mortals have really started to appreciate it. And I certainly don't feel like I've really absorbed it, you know. I mean, they're still, you know, they're always, you know, little puzzles that you can, if you think about it too hard, you just, you know, how can this be true? But yet it seems to be true. And I think there are still many more things that we need to understand about this. Actually, I want to emphasize that I really, you know, although I motivated this discussion with the interiors of black holes, and we have learned some things, we haven't learned everything, or we haven't learned the most important things. And so here are a few questions which I really want to know the answers to, but I don't. So what is the bulk mechanism by which information which falls into a small black hole is transferred into its Hawking radiation as it evaporates? Okay. What is the experience of an observer who crosses the horizon of a large ADS black hole in a typical pure microstate? That's the question that Ahmed requested, so since no one asked it, I'm asking it now. And in particular, can that experience be described using ordinary quantum mechanics or not? What is the bulk dynamics which accounts for the long-time fluctuations of thermal correlators in the spectral form factor? That was something several people mentioned in their talks. And one of my personal favorites, so at really absurdly long times, if you take the thermal field double and you evolve for a doubly exponentially long time, there's a quantum recurrence and it becomes short, the bridge becomes short again, right? And obviously that's not a property of the ADS Schwarzschild solution. That's some crazy feature of quantum gravity, and you know, it's hard to even begin to think about what the bulk process is whereby that happens. Now, since this is a vision talk, I want to close by making a few speculations about where progress might come from. Obviously, these are speculations, so no promises. So the first is that I think we need to understand better the fact that in gravity, time translation is a gauge symmetry. So let me give an example. So, you know, this is the thing everyone loves to do now. You take the two-sided wormhole and you evolve with the Hamiltonians to the future. But actually, if all you do is do boundary evolution, you know, why don't we just say you're just evolving from this slice to this slice? Right? Doesn't know about the interior at all. You know, how is this slice, you know, I mean, maybe you like this slice, but how is it any different from this slice? In fact, the difference between this slice and this slice is a gauge transformation. It acts trivially on the Hilbert space of the CFT. So somehow if we, you know, I want to emphasize, I mean, the evolution, you know, at least I really care about is the one from here to here, right? This one is just kind of, you know, whatever. You're just doing, it's just all happening in the exterior. And I think that to really learn how to describe the interior directly in the CFT, we somehow have to deal with this fact that this thing that seems super important is just zero acting on the Hilbert space. So somehow we need to learn how to ask about the interior using diffeomorphism and variant observables. So that's one comment. Secondly, I think we need to move beyond what I sometimes call the cult of the thermofield double. So I love the thermofield double. We all love the thermofield double. It's very useful. You can compute all sorts of things, but it's a very special state. In fact, I think for thinking about the black hole interior, it's somewhat analogous to the state where all the air in this room is just, you know, up in the corner over there. Right? It's a very atypical situation. And one way of seeing is that it has this funny property that the causal entanglement wedges of either boundary are equal, you know, whereas generically the entanglement wedge is bigger. And that's what makes it possible, for example, to just drop in a penny from the left side and see it immediately as soon as you cross the horizon on the right side, right? That's something, if you think that it's always easy to do that, you might believe, for example, there are firewalls, right? But then actually generically it seems like it's harder to do that. So these solutions of Schenker and Stanford is one laboratory for exploring what happens when you go beyond this, and I think we should stress test more of our ideas in those solutions and beyond. This is my last slide, so don't worry. Actually, I think second to last. Thirdly, I think that the formalism of approximate quantum error correction is a very promising avenue. So far, most of the results have been based on exact quantum error correction. But approximate quantum error correction is also quite well developed, and actually even now, more things are being developed. And I think it's probably a useful formalism for understanding this idea that the emergence of bulk effective field theory is approximate, and you can have small errors, but then somehow they can accumulate if you ask sufficiently complicated questions. And in particular, there was a paper by Hayden and Pennington about what they call alpha bits, which seems like it might give a quantitative formalism for understanding this sort of accumulation of the small errors leading to a large error if you ask something complicated. Finally, I want to mention some of what Ahmed already talked about today. So that was a very thought-provoking talk. So that was based on this idea of the quantum extremal surface of Netta Engelhardt and Aaron Wall, which is a generalization of the RT formula to higher-order effects. And so there was this recent work which Ahmed was talking about. I don't quite understand all of it, but it seems very, even if I don't quite know what the final message is, there's clearly something very interesting going on in this work. I think there's something powerful brewing there, and I bet you that we'll hear more about it at Strings 2020. Okay, I just wanted to close. I'm reasonably optimistic that we'll see resolutions of at least several of these problems in the next few years. And my real hope is that we'll eventually be able to use it to move on to cosmology and understand de Sitter space, which I guess I still think exists, at least metastable, and hopefully to closer connections with experiment, which I still think is a very important thing. Okay, thank you.
Okay, thanks. So there are one or two questions for you, which you carefully avoided in your talk.
Oh, did I? Okay.
So one of them is, so what does this reconstruction in the bulk say about black hole singularity or cosmological singularities?
Well, yeah, let me make a comment about that. So sometimes people say that the real mystery of quantum gravity is the black hole singularity. Now, I'm actually a bit of a contrarian on this subject because I can't think of a well-posed question that I want to know the answer to about the black hole singularity. Because if I go near it to try to do an experiment, it's just not a very pleasant experience for me. So I think one of the really nice things about this idea of talking about the firewalls is that there's a real experiment. You jump into the black hole, the curvature is low, we could even do it, in the real world, and you want to know what you see. I guess with the singularity, I don't know. I mean, everything is just Planckian there. I mean, I think it's important to focus on questions that that are related to experiments we could at least imagine doing. And maybe there is one, but I'm not sure I've been able to think of one.
I think you're avoiding the question again. So this was asked, I won't reveal the author, but someone who's thought about this deeply.
Yeah.
You were saying that you'd like to use ADS-CFT to ask questions about what happens to an observer who falls into the bulk.
Yeah, but I found there's already a paradox at the horizon, so I guess I feel better about making progress on that one.
Right.
Yeah.
Yeah, but the question wasn't about the
for the singularity.
avoiding,
well, I just don't know. I don't have anything to say about it, but I don't even have a question. Yeah, I mean, not only do I not have answer, I don't have a question.
Our question was, what does space-time reconstruction say about the black hole singularity?
Well, okay,
but
I don't know.
Let's switch to something which the experiment presumably has already been carried out, which is the cosmological singularity.
Yeah. Well, of course, I can't directly address that in ADS-CFT in a simple way. There are various attempts to, turn on various deformations and create things that look like cosmological singularities in ADS-CFT. And I guess my state of ignorance about those is similar to my state of ignorance about the Schwarzschild black hole. In the real world, the only thing I can say is that my favorite scenario for the Big Bang is that we're living inside of a bubble, in which case the Big Bang is a coordinate singularity.
We might come back to that in the discussion. And the other, there were one or two questions which really were similar. About space-time reconstruction and quantum mechanics. So does the space-time reconstruction require violations of quantum mechanics in the usual sense in terms of state-dependent operators?
Yeah.
And is that a disaster for quantum mechanics in some way? Does the proposal require a modification of quantum mechanics?
Well, so state dependence is often a term that one hears these days. There have been several attempts to say what that actually means. None of them, I would say, are really complete or even self-consistent. I certainly think it's possible that quantum mechanics will need to be modified to describe the experience of the unfolding observer. And perhaps my favorite reason for that is because there are all these puzzling things about what measurements mean in quantum mechanics, and the only way I know how to think about it is that you have this observer who's external to the system and has sort of as much entropy available to them as they need to really measure the system as precisely as possible, as many times as possible, and then I know what these probabilities mean. But for the observer inside the black hole, they're fundamentally limited in the resources that they have available to them. So for example, I think such an observer probably doesn't really have the right to a probability distribution constructed out of real numbers, because what would it mean? They couldn't really confirm it. But this is just some vague comment, right? I mean, and in terms of the more detailed modifications that have been proposed, some of them may be along the right track or not. I mean, they're kind of not we can't really tell because none of them are really self-consistently formulated yet. But I'm certainly open to the idea. At a minimum, it'll have to be like approximate quantum mechanics. So that already sounds like a new thing, whatever it is.
Okay, we might come back to that in the discussion after Douglas's talk. Let's thank Daniel. Let's open it up for immediate questions pertinent to Daniel's talk. Edward?
So you think, is that true? I admit I don't know much about Kerr. It's somewhat embarrassing. So you mean it's easy to get, there's an experiment that's near the singularity in Kerr? There's weak curvature near the singularity?
Relativists are working on it, so it's hard to say the outcome, but it's not clear that you can't travel to a region where you can see the singularity.
I see what you mean. You mean about this, whether the mass inflation singularities or whatever? Yeah. No, that's true. So I guess I have an implicit bias, which is that once you include quantum effects, the singularities will always be space-like. But probably my arguments for that are mostly emotional, so I don't think I should argue for it too strongly.
Could you maybe share your vision on vanishing cosmological constant?
Oh, you're asking about flat space?
Yes.
Yeah, that's an excellent question. So indeed, if de Sitter space is too hard, we should first understand flat space. And actually, a lot of people have been thinking about this from the bulk point of view in the last few years, trying to understand what are the asymptotic symmetries in flat space. Something which I think is missing from the discussion so far is this BFSS matrix model, which is at least claimed to be a holographic description of asymptotically flat 11-dimensional quantum gravity. All the mileage that we got here came from actually knowing that the CFT was there and somehow using the axioms that we know it obeys, even if we can't solve it. And I think a similar effort has not been made with the BFSS model. So I think that's something that, is very promising. If I wasn't already sufficiently confused in ADS to stay there, I would certainly be working on it.
It's quantum mechanics, no.
Yeah.
Not a CFT.
Yeah, so it seems better on some level, but it's confusing quantum mechanics.
Okay, let's thank Daniel again. And